My name is Justin Braun. I'm from Sensoron. I'm doing a presentation on VITA COTS hardware and how it simplifies the design of high-end instruments. I'm very happy to be here because usually when we do these types of presentations or do presentations for our company, it's all about the applications and not the engineering behind it. We'll start with doing an introduction about who Sensoron is, and then we'll get into what fiber optic sensing is and specifically what OFDR is. It's a type of fiber optic sensing. And then we'll go into 2 case studies on our RTS-150 and then our RTS-125 and kind of how the hardware evolved and how this COTS hardware, standardized hardware, helped us realize our instrument. And then we'll go into a discussion on how we can move forward using some of the VITA standards. So Sensoron's headquartered in Austin, Texas. It's a privately held company. We spun off from 4DSP about a year ago. And we have the fastest OFDR fiber optic sensing system available on the market. We work very closely with NASA, NASA Armstrong. And we were the winner of a R&D 100 award in 2013. Our industry focus is in aerospace, automotive, energy, and medical. Why fiber optic sensing? What is fiber optic sensing? What we have, fiber optic sensing is using a fiber optic cable as a sensor, analogous to a strain gauge and a thermocouple for temperature measurements and strain measurements. And on a fiber, we can actually get about a couple thousand sensors on there. And that allows us to do efficient distributed sensing. So in addition to that, with the strain measurements, from the strain measurements, we can also derive 2D and 3D shape sensing. And what I want to point out here is, this is a traditional strain gauge, and that's a traditional thermocouple. And then right here, you see a fiber optic cable bonded to this aluminum plate. And we just have a single fiber optic cable, but for every strain gauge and every thermocouple, you have to have copper wiring going to each one of them to make that single point measurement. So it ends up being a bit of a mess. So for 21 strain gauges, that's the amount of wiring that you need, and you have to send it back to some kind of instrumentation to actually interrogate and make the measurement. This black line right along here that you can see kind of zigzagging across this plate, that's a fiber optic cable bonded to that plate, and we're making measurements all along that fiber optic cable. In fact, we have 628 sensors. And then to actually get that information back to our system, it's a single fiber optic cable lead that goes to our instrument instead of that bundle of copper cable. So there's also some other benefits, like it's got immunity to EMI, it's embeddable, stands up in harsh environments, high temperature ranges, and it provides an absolute measurement, unlike strain gauges. So OFDR, so we're talking about building the instrument, and so I wanted to introduce the architecture of the instrument. We have a swept wavelength laser that provides a light source, and that light source is passed through some optics, it goes through the front I/O, and it's sent out to our fiber optic sensors. And each one of the sensors, thousands of sensors on each one of the fiber optic cables, reflects light back that tells you what the strain or temperature measurement is at that point. And the neat part about it is, along the fiber, every one of these is encoded through frequency. So we end up doing a lot of frequency analysis in our FPGA, and that's how we can tell exactly where this measurement or where each one of these sensors is located. And then there's a little bit more processing that we do to actually derive the strain information and temperature information. So the signal's reflected back from those sensors, and it passes back through the front I/O into the optics. It goes through optical to electrical conversion, then it goes to ADC, and from there that digitized data is passed to the FPGA, where a bulk of the processing is done, and then it's finally passed through PCI Express to a processor, where it's packetized and then transmitted out to a client machine monitoring the information. So we do use an FPGA in here, and it's pretty neat, the parallel processing for the DSP operations. is equivalent. I think our NASA partners were having to use a cluster of computers to try to get real-time data. And in a small FPGA, we're able to do the same computing and actually have it in an embedded system and not in a rack of computers. So the RTS-150 was the first product that we produced, and it was based on COTS hardware. We had been working with this chassis for other projects at 4DSP, and we were kind of used to it. You know, it has a VPX backplane. We have a VPX small board computer, which is right there and right there in the leftmost slot. And you know, in the early prototyping stages, we had 2 VPX cards, FPGA cards for the processing. Each one of them had their own FMC that had ADCs on them. And then we also had the optical to electrical conversion, which was located on these plates, and those were custom boards. But the point is that we were able to buy a lot of this hardware off the shelf, get our prototyping needs done, kind of prove out the concept, and then we began to iterate on the design. And from there, we ended up taking these optical to electrical conversion cards. You know, there's a total of 8. You can't really see them in there, but we condensed them all down into 2 FMCs. And so that FMC standard, you know, putting it into that FMC standard, and then we were able to consolidate all of that into just this section right here. And we were also able to, over time, after we proved out the concept, iterate on the FPGA design, condensing it down, and reduce the amount of hardware that we needed. So instead of 2 high-dollar VPX FPGA cards and 2 high-dollar FMCs, we got down to 1 VPX FPGA card and 1 FMC for that. So there was a dramatic reduction in cost. So the other point is, you know, that's kind of the nice part. There were also a number of other non-standardized products that we had to integrate into the system, and that was all kind of difficult. You know, it's not easy. The VPX standard allows you to just slide in these cards, and with a BSP from whoever produces the cards, you can get up and running and get your design integrated and kind of prove out the concept. But we have, you know, a COTS laser, but we had to, you know, do a lot of mechanical design to get it mounted inside the system. The optics were all custom, so that was kind of a mess. And then, yeah, you know, it was a lot of work to get it all integrated together, but the COTS components made it easy and helped prove out the design. As we were able to iterate through the design, we also realized that we could go with a smaller or a cheaper small board computer, which also saved on cost. And overall, you can see, after iterating on the design and converting these cards to FMCs and then integrating them into the final production system, it cleaned up things, and it's a lot easier for production and assembly. The RTS-150 was a decent instrument for us, but we had a lot of customers interested in a ruggedized system, you know, that they could bolt onto a plane or onto a car and make active measurements on those types of vehicles. So we decided to invest some time, because we had some confidence in the RTS-150, into developing the RTS-125. So because of the ease that we had doing the prototyping with the RTS-150 and introducing that system, we were able to actually spend more time on customization for this product. And we actually created a set of stackable FMCs, which you can see right there. And they're also located right there in the final system. And so we actually moved from a VPX FPGA card to an FMC FPGA card. And we also developed a FMC card that was kind of a carrier for another standard, Q7, which is a small board computer as well. And that resides at the bottom of the stack. So now all of our processing was able to be condensed into this small footprint. But we did have to also undertake building a custom frame, which before we, with the RTS-150, it was off the shelf. We had off-the-shelf cooling, off-the-shelf power, everything was included with that chassis, so it was all easy. So, but here we had to improvise and to condense things down. It allowed us to, the proof of concept kind of allowed us to spend more time and resources on customizing this box. These are all VITA standard FMCs here in the stack, and we were able to get a lot of design reuse as well. So the FPGA design with the BSPs from who we purchased the boards from, it was fairly easy to migrate the design. We had all the interfaces to all the I/O that we needed, and then the actual DSP portion that kind of operates in the middle of the FPGA. It was easy to move that design over here. And then we were able to reuse what we kind of developed. Well, we reused our FMC, the ADCs, and then the FMCs that perform the optical to electrical conversion. And what this also allows, this modular design at this point, eventually we want to get to a full custom design. But this modular design, as we're still trying to improve the overall system quality, we would like to, we can sit there and operate or do design revisions on a single board instead of on an overall custom design. So moving forward, with the modular designs that we have right now, it's easy for us to upgrade parts and make design revisions to individual parts and substitute them out. Scaling hardware in our RTS 150, that was an 8-channel system, 8 fiber optic channels. And then we were easily able to scale to 16 channels by adding just another VPX card, duplicating the VPX and FMC cards that we had in the system. For the FMC stack that we have, we can also increase the number of layers of FPGA processing, the optical to electrical conversion, and the analog to digital conversion cards. And you can scale that up. And we could use something like SFPDP to get the communication between the FPGAs and eventually propagate the data down to PCI Express to the small board computer where it's sent out to the client machine. We're also looking at using VRT. Timestamping is particularly important to our customers. The laser that we use is kind of mechanically driven, and it's not periodic necessarily. And because it's not periodic, you can't rely on when each of these measurements were made, and that's causes problems for some of our customers. So we're looking at actually including VRT timestamping within our system to provide them with that information. And then with that stack of FMCs, what we can also do is 4DSP leveraged that technology, and they actually take that stack of FMCs. They don't use the optical to electrical conversion, but they were able to make a conduction-cooled box for it, for VITA 75, and we can actually kind of leverage that as well and integrate it in there. But I think the neat thing is that technology that we developed for this RTS 125, the ruggedized system with a stack of FMCs, actually led to launching of other products at 4DSP at the time. The pros and cons of leveraging the COTS VITA standard products. You don't have the NRE costs of developing this hardware initially. You're able to buy it off the shelf. There's a reduced integration effort, like I mentioned in the RTS 150. It was perfect for prototyping. Time to market was decreased dramatically. And taking advantage of things like the BSP also helped out quite a bit, because if you're doing a custom board design, you're also having to do the FPGA design completely from scratch to get all your interfaces up to memory and to the FMCs. But we were able to kind of circumvent those developments, leveraging the BSPs provided by the manufacturers. Also, with the VITA standards like SFPDP, there's interoperability, so communications between systems. That helps out a lot. Someone designs to a standard, someone else designs to a standard. You can communicate easily between the systems. Repair at this point, modular. So we get it back, an RMA for one of our systems back, And all we have to do is remove one of these modules and replace it instead of replacing a full custom board. Also, modular upgrades. As things change over time, there might be new FPGA devices or a new ADC card that's introduced that might provide better performance, and we can actually substitute those components out in our system and maybe introduce a better performing product line. And as I mentioned, from the development from our RTS-125, 4DSP was able to leverage that development, the FMC stack, and create a couple other products based on that development. And it's a standardized development. So the cons are you have lack of control and ownership of some of these parts that you buy. It's not as efficient. That RTS-150 was very bulky. The chassis was very large. There was a lot of unutilized space. And power consumption is also not as efficient. And for large volumes, it's not as cost effective. But time to market is very important, and being able to prototype easily is very important. So that wraps up the case studies. But here's a couple of pictures of what we're able to do with our system. This is a cryogenic liquid container. And NASA is using the system to measure the liquid level within this container. We have composite structures, and we have fiber embedded within these composite structures, and on the surface, and they're able to make measurements and see how stresses occur as they start to increase pressures within these tanks. And then a flat plate like this, you're able to interrogate it. You might have a finite element model for a plate like that, but then it provides design validation for this. You're able to actually measure and see how the two match up, your measurements and your finite element model. And then finally, some of the more interesting things are the 2D shape sensing. You bond these fibers on these plane wings, and you're able to see the deflection of these plane wings and see the stresses on these planes. And then also 3D shape sensing. You can see this fiber optic cable. It's actually got jacketing, so it looks rather large, but we're able to show the 3D shape of that fiber optic cable. And that's used or could be used in medical applications, all sorts of applications. So a lot of people don't know the 3D shape of their structure.